Okay, so we've been talking about sequences. And what we're usually interested in, of course, with sequences is what happens as n goes to infinity. Do these things converge? So we have a definition of convergence. We have some techniques for proving convergence. One of the big challenges probably of using our definition of convergence, the definition of the limit, is that if you're going to prove that something has a limit using the definition, you first have to sort of know what the limit is, right? You have a sequence, and then you have a guess at what L is. You try to prove this converges to L. That's great if you know what L is, or if you have a reasonable way of guessing what L is. In real life, you usually don't know what L is ahead of time, because again, a lot of these sequences might come from doing some kind of computational thing like Newton's method. And if I knew what the limit was ahead of time, I wouldn't be doing this iteration. I'm doing it because I don't know what the limit's supposed to be. So what you'd like to be able to do is take your sequence, prove that it converges, but someone will be able to prove it converges without actually knowing ahead of time what the limit is going to be. So this is the challenge we're going to sort of look at today. We have a definition of the limit. So how can we prove that a sequence converges? Okay, without needing to actually know the limit. Okay, in particular, what we want to be able to have is some way of verifying convergence that just looks at terms in the sequence. Because terms in the sequence we can compute, we can learn things about. So the first thing you might think to try is, well, we have terms in the sequence. Are they getting closer together, right? If they're getting farther apart from each other, then they're probably not converging. So this might be the first thing you want to check. So are the terms in the sequence getting closer together? So we'll say it this. Are they getting close together quickly enough? Okay, so this is the first thing you might look at. Can we learn anything from, say, looking at subsequent terms? So Sn minus Sn plus 1. And as n goes to infinity, if this sequence is converging, we should expect that all of these, right, this term is getting really close to S, this term is getting really close to S. So the difference between these things should be going to 0. So what would you guess if you had to make an educated guess? Is this a good enough condition for convergence? Is it a reasonable condition? What do you think?
I guess necessary but not sufficient.
You guess necessary but not sufficient. Okay. Anybody want to argue with that? All right. So let's try an example. So S1 equals 1. Okay. It's certainly a necessary condition, right? Because if these are converging to S, then the difference between them is going to 0. So it's definitely a necessary condition. And let's define our sequence this way: 1 plus 1 over n. Okay, so S1 is 1. S2 is going to be 1 plus 1. 1 plus a half. S3 is going to be 1 plus a half plus a third, and so on. Okay, and we can check that Sn minus Sn plus 1, right, is going to be 1 plus 1 over n minus 1 plus 1 over n plus 1 let's see, is this the way I want to write it? This should probably be Sn minus 1. Let's try this. Okay, and what do we get? This is the difference between subsequent terms. So we get Sn minus Sn plus 1 over n plus 1. Right, so if I look at the difference between them, I can leave Sn the same. Because this is defined recursively, I can put Sn plus 1 in terms of Sn. This is 1 over n plus 1. And this certainly goes to 0 as n goes to infinity. Okay, and what do we know about this sequence? You should recognize this sequence. Right, so again, S1 is 1, S2 is going to be 1 plus a half, S3 is going to be, okay, the old guy 1 plus a half plus a third and so on. What is this looking like? This is looking like the harmonic series, right? So in general, we're going to have Sn is equal to the sum, k equals 1 to n of 1 over k. Okay, but we know, okay, we haven't proved this yet, we will prove it, but we expect from what we've seen before that this doesn't converge, right? It's not converge, or it's not expected to converge. Okay, and that's because this is indeed the harmonic series. Okay, so this condition here, this condition might be easy to check, but it's not good enough to guarantee convergence, right? If this condition holds, we might have convergence, but as in this situation, we might not have convergence. So we need something else, but again, we're still trying to do something that's easy to verify, something that doesn't require us to know this limit ahead of time. So we're going to take this condition and just try to modify it a little bit so we have something that's still fairly easy to work with. So modification number 2 is to say comparing next door terms doesn't work. It's not good enough. But maybe if we compare arbitrary terms, if n is big enough, not Sn and Sn plus 1, but maybe Sn and Sm for some much larger value of m, maybe if that difference is small, it's good enough. So not only are the neighboring terms getting close together, but as n gets big, all the terms after that value of n are getting close together. This would be the idea. So let's try checking this. Let's compare arbitrary Sn and Sm for sufficiently large values of n and m. So instead of saying, great, S100 is close to S101, we'll say, OK, S100 is close to S200, and S100 is close to S5000, and all of these different things are close together. So maybe that's good enough. OK, so this is going to be what we call a Cauchy sequence. So a sequence Sn, OK, of real numbers, is going to be called a Cauchy sequence. If okay, and now we're going to build up a definition that looks similar to the definition of our limit, but instead of saying that Sn converges to S, instead of using that definition, we're going to try to make the claim that Sn and Sm converge to 0, that they get very close to each other. So we're going to still have, for every epsilon greater than 0, and then our usual definition of the limit says there should exist some n star such beyond that n star, Sn gets close to S. That's what we expect. So instead of just taking a single point bigger than this, we're going to take two values closer than this, any two values. So it could be maybe n star is 100. We could take 101 and 102, but we could also take 101 and 10,000. Or we could take 500 and 806, whatever. Any two that we like that are bigger than this n star, then we should have that the terms in the sequence are close together, as close as we like, less than this epsilon tolerance. Are there any questions on the definition? Of course, we're going to practice using it and then try to convince ourselves this is actually a useful thing to deal with. But does the definition itself make sense? Okay, so if we go back to this harmonic series example. Okay, so Sn was 1 plus a half plus a third all the way down to 1 over n. Okay, so we're going to try to do the thing where we hopefully break this definition. That's what we want to be able to do. So what that should mean is that there exists some epsilon, we'll decide later what that is, such that no matter how big I choose n star, I should be able to find an n and m that make this difference bigger than my tolerance. Okay, so let's choose any n star as big as we like. And take, okay, m bigger than n star. Okay, we'll decide later what exactly these m and n should be. But the key thing is that this n star, I'm saying, is no matter how big we take it, we're going to try to show that we can break this. Okay, so I've got my n star. I need to look at these terms. So we're going to try to compare these terms. Of course, when I look at Sn and Sm for different values of n and m, one is bigger than the other. It doesn't matter which is which, so I'm just going to make the assumption that m is the bigger one. It makes no difference to the definition. So we look at these two. Sm minus Sn. Right? So this is going to include 1 plus a half, everything up to 1 over n. This is also going to include all those terms plus a bunch more that go beyond 1 over n. So this is going to leave us with 1 over n plus 1 plus 1 over n plus 2, all the way down to 1 over m. Okay, so m is the biggest of these denominators, yes? So that means that this term is bigger than 1 over m, right? M is bigger than n plus 1, so 1 over m is less than 1 over n plus 1. Same with this guy. Same with this guy. Okay, so now I'm trying to simplify things, right? With all of these, we never need these things precise. We just need bounds that will give us the result we want. This makes life easier because I have the same term a bunch of times, which I can add up. How many of these do I have? N minus m, yeah. So there are n minus m of these. So this is equal to n minus m times 1 over m. M minus n, thanks, yeah. Yes?
I'm confused by like the 1 plus m
Right, so what I'm saying is I have a whole bunch of terms that I'm adding up here, right? And what I'm saying is that we've assumed that m is bigger than n, right? So this is n plus 1, n plus 2, all the way. They're growing until they hit m. So since m is bigger than n plus 1, right, that means 1 over m is going to be less than 1 over n plus 1. Right, we can do that on the side here. So m is bigger than or equal to n plus 1. That means 1 over m is less than or equal to 1 over n plus 1. So I'm doing that comparison with these terms. Then I'm doing the same comparison with n plus 2. Okay? Same comparison with n plus 3. I keep going all the way until I get 1 over m is now equal to 1 over m, but certainly greater than or equal to. Okay, so this is equal to 1 minus n over m. Okay, now we have a little bit of freedom in how we choose this m and n, right? We've said n star is as big as you like. I'm going to choose some n that's bigger than this n star. And I'm going to choose some m that's also bigger than that, and that's bigger than n. So here now we take n be bigger than our n star. And m, what would be something reasonable we could take m to be? 2n, right? Just something simple, because again, I'm trying to simplify this and not have so many things floating around. I want it to look simple, something that I can estimate easily. So I could take this to be 2n, for example, which is indeed bigger than n. And what do I get? Sm minus Sn is equal to 1 minus n over 2n, which is a half. Greater than or equal to a half, yeah. Right? And this it doesn't matter how big n star is, right? No matter how big I take n star, I can always find a choice of n and m such that the difference between these two things is at least a half, right? I could call this my epsilon. And this is us breaking this definition here, right? Instead of saying for all epsilon greater than 0 this works, we've said now we found an epsilon. Epsilon is a half, such that there just is no n star that makes this work. No matter how big I take n star, I can always choose n and m bigger than that to break this inequality. That's exactly what we've done right here. So this sequence that we wrote down, where we said, OK, the neighboring terms, they get close to each other, right? Sn minus Sn plus 1, that goes to 0. Next door terms do. But if we start saying, let's stretch things out and not look at next door terms, those terms don't get arbitrarily close to each other. So we're going to conclude this is not a Cauchy sequence. Okay, so that's good. We're proposing this as some kind of technique for trying to check if a sequence is convergent. We haven't proved that it works yet, but at least it sort of passed this test case, right? This test case where our first criterion failed. So it's at least it's still in the running as a good criterion. Any other questions on this example? Okay, so that was a failure of the definition. We can also try to do an example where hopefully the definition actually works for us. Okay, so another example would be Sn equals 1 minus Rn plus 1 over 1 minus R, where R is less than 1 in magnitude. Okay, this we've seen before, right? This is the sum of the geometric series. And you can prove that by induction. This is the sum of the geometric series. Okay, we also happen to know that this is a convergent sequence. because here, we could just take the limit directly, right? We take n to infinity, r is less than 1, so this term goes to 0, and we get 1 over 1 minus r. So we already know this is convergent. What we'd like to see is it a Cauchy sequence? Does it also satisfy this condition where the terms get close together? Okay, there's a sum of geometric series, and we know it converges. Okay, so the real question is just how do we check that this thing is Cauchy? Let's verify it's a Cauchy sequence. All right, line 1 is always the same, right? We have this definition. It says for all epsilon greater than 0, something has to hold. So line 1 is let epsilon be anything bigger than 0. Okay, and we know we're going to have to look at neighboring terms. So let's pick any m and n, and we'll decide later how big they have to be. So let's look at m that's bigger than n again. Okay, and we're going to try to look at the difference between these terms. So now Sm minus Sn is equal to 1 minus Rm plus 1 over 1 minus R, and 1 minus Rn plus 1 over 1 minus R. Okay, this we can bring over a common denominator. We get Rn plus 1 minus Rm plus 1 over 1 minus R. Okay, again, we'll try to simplify this to try to force this to be less than epsilon. And as a general rule of thumb or strategy, it's not that convenient having all of these different n's and m's floating around, right? It's nice to try to put this in terms of things that we can more easily force to be less than epsilon. So we're going to do our usual tricks. One of our usual tricks is just to try to factor things to start with. In particular, right, we've got r to some power minus r to some power. We can pull out all the common powers of r. We know that m is the bigger one, so we could pull out the Rn plus 1. Okay, so I'm going to get Rn plus 1. Oops. Okay, and then times whatever's left. Whatever's left is 1 minus r to the m minus n divided by 1 minus r. All right, r to the m minus n. M minus n is a positive exponent, yes? We've made sure of that. How big can this be? What's the biggest that could ever be? So r to the m minus n, what's the biggest that would ever be? 1, right? R is less than 1. So when we take something less than 1 and raise it to a positive exponent, we're going to get something that's less than 1 in magnitude again, right? And so we'll put this over here. We know that r to the m minus n is certainly less than 1. And it's going to be bigger than minus 1, yes? So what's the biggest that this numerator is ever going to be? 2, right. So what am I going to have? I'm going to have 2 times r n plus 1 divided by 1 minus r. Okay, again, 1 minus r we know to be positive, so I can drop the absolute values. And what's our goal? Our goal is to make this less than epsilon. And now we're in a position where we can probably do this, right? We've simplified this down to where n is only appearing at one point in here. And that's usually the place where we can say, now I can try to solve for what n has to be. So this is a good time to say, can we make this less than epsilon? And we can, right? As long as, if I rearrange things a little bit, r to the n plus 1 is less than epsilon times 1 minus r divided by 2. Okay, I can take the log of both sides. The log is this monotone increasing function. So if this is less than this, then log of this is less than log of this. So that's always safe. So this holds true if n plus 1 log r is less than the log of all of this. So what kind of condition is this going to give us for n? So, okay, are you you're worried about the direction of the inequality? Are you? Log r is negative. That's important here, right? So r is less than 1 in magnitude, right? Log of 1 is 0. Log of something less than 1 is negative. That's important. This term is negative. So that means when I divide it out, this inequality is going to flip. That's important. So this is true if n is bigger than, now the inequality flips, log of all of this, okay, divided by log of r, and then I'll subtract off the 1. If a condition came out to say this only worked for small values of n, then we'd be hooped, right? But it didn't. It came out right. It says this works. We can make this less than epsilon as long as n is big enough. So this becomes my n star. Okay, and that was all we needed, right? We needed to be able to find an n star such that as long as m and n are bigger than this, so n is bigger than this, m we said is bigger than n. So as long as m is bigger than n and n is bigger than n star, we indeed have that Sn minus Sm is less than epsilon. Okay, and this is exactly what it means for a sequence to be Cauchy. So we're going to conclude that Sn is a Cauchy sequence. Questions there? Right, so it's not substantially different from how we'd use the definition of the limit, right? This epsilon and n star definition of the limit. The one extra bit you have to worry about is that you have both an n and an m floating around. And this would be typical kind of reasoning to say, can we put some bounds on here that put this all in terms of n or all in terms of m, something like that. And then you're back to just doing the same kind of calculations you would normally do when you're working with the definition of a limit. Okay, so this was a sequence that was known to be convergent. It is Cauchy. We had a sequence that's known to be not convergent. It wasn't Cauchy. That proves nothing, but it says at least this concept of terms getting closer together is at least, again, still in the running. It's still reasonable on these examples, but we need to try to prove some things. So what in the world does this have to do with checking convergence? So we have a couple results on this. One is that if a sequence of real numbers converges, then it must be a Cauchy sequence. Okay, this one should be not too hard to check. So we're going to start by writing down what we know. We're going to let Sn be a convergent sequence. And it has a limit S. Okay, that means if we choose any epsilon greater than 0, so again, I'm just doing what I always do. I'm writing down what I know. What I know is this thing has a limit S, and I'm going to write that down in terms of what the definition of the limit means. So that means there exists some n star such that if n is bigger than n star, then Sn minus S had better be less than epsilon. Okay, now what we want to do is check that this is a Cauchy sequence. So that means we need to look at generic m and n, right? So we're trying to show that given this epsilon, there exists an n star. This looks like a good candidate for our n star since it happens to be floating around. But we need to look at two numbers now, not just n, but m and n. So let's choose any, okay, m and n that are bigger than n star. And we need to compare these terms. So Sn minus Sm. And how should I rearrange that? I should probably add and subtract an S, right? This is the thing we want to look at, but this is the thing I know how to work with, right? Sn minus S, and m is also big enough. Sm minus S is also fine to look at. So I should put this in terms of things that I know how to deal with. So I'm going to write this as Sn minus S plus S minus Sm. I haven't changed anything, but now I've got terms floating around that look familiar to me. And this is hopefully not surprising. I'm going to do triangle inequality. Right? So I'm going to say this is less than Sn minus S plus S minus Sm. All right, we've chosen these to be big numbers. So m and n are both bigger than this n star, and that means this estimate holds for both of them. So this is less than epsilon plus epsilon, which is 2 epsilon. And that's good enough, right? So I can make 2 epsilon. 2 epsilon is my tolerance now, and I can make that as small as I like, right? No matter how small I make this 2 epsilon, I can find an n star that will make this work. So again, that's good. As long as whatever I end up with here on the right-hand side goes to 0 as epsilon goes to 0, we're happy. So we're going to say, indeed, Sn is Cauchy. Okay, so we know every time I hand you a convergent sequence, you know automatically it has to be a Cauchy sequence. What happens if I hand you a sequence and you look at it and you say, oh, but this is not a Cauchy sequence. What do you know about it then? It's not convergent, right? So if convergence implies Cauchy, then anytime you have something that's not Cauchy, it means not convergent. So this is an immediate corollary of this. If Sn is not Cauchy, then it's not convergent. Okay, so this is one test for does a sequence diverge, right? Okay, you could run through the definition of the limit and show that it breaks no matter what you choose the limit to be, no matter what you choose S to be. Or you could show that it's not Cauchy, that the terms don't get close together. And if you can show that breaks, then you right away know this is not a convergent sequence. It's not going to do what I want it to do. Okay, so that gives you a test straight away for non-convergence. Of course, we also want a test for convergence. A test for non-convergence is useful because it could tell you that the method you're trying to use, the numerical method you're trying to use, is no good. It's not going to do what you want, and that's useful information to know. Okay, but we still want to test for convergence. So I'm going to give you a lemma, and then we're going to prove that this idea of the Cauchy sequence actually does correspond precisely with convergence. So let's start with a lemma, right? A lemma is like a little mini theorem that we don't care about that much on its own, but we're going to use it to prove something that we do care about. So if Sn is a Cauchy sequence, then it is bounded. Okay, I'm going to do this by contradiction or contrapositive, whatever you'd like to call this argument. I'm going to say, let's suppose actually Sn is not bounded. Okay, so we're started with the sequence that's Cauchy. I'm going to assume it's not bounded and show that that leads to a contradiction, that actually then it's not Cauchy after all. Okay, so we're going to break the definition of the Cauchy sequence. Okay, so let's look at any n star. Again, it can be as big as we want. Okay, and any n bigger than n star. All right, we want to show that no matter how big this is, no matter how big this n is, I can find another m that's also super big, such that Sn minus Sm just stays large. It doesn't go to 0. So this is our goal. Okay, so we look at Sn. We want to try to find, so we want to find m bigger than n, such that Sm is in some sense not close to Sn. Okay, does such an m exist, or how can I find it? What information have I not used yet? Right, we should use the information that we know. we've assumed it's unbounded, right? So what does that mean? That means I can find a term. Okay, Sn is whatever it is. It might be huge, I don't know. But I can find another term that gets even huger, always, as big as I want. That's what it means for something to be unbounded. No matter how high I put the ceiling, I can find something that jumps above it. So this means since Sn is unbounded, there exists some m such that Sm in magnitude is bigger than Sn plus 1, say. Okay, so Sm and Sn are not close together now, right? They differ by at least 1. We can write that down. Sn minus Sm. Okay, this is, we've seen this before, a rearrangement of the triangle inequality. I should do this the other way around. Sm minus Sn, which we know is bigger than or equal to 1. Right? We designed Sm to be much bigger than this, at least 1 bigger than this. And now I'm going to call this my epsilon. So again, we've taken the definition of a Cauchy sequence, we've turned it on its head, and we've said it doesn't work, right? There's some epsilon out there such that no matter how large I take n star, I can always construct an n and an m that are bigger than that, such that the difference between these terms does not get less than my tolerance. It stays bigger than my tolerance. That's breaking the definition. So this says Sn is not Cauchy, which is a contradiction. Right, so this is our usual proof by contradiction. We started with a Cauchy sequence. We said, let's assume it's not bounded and just follow the consequences of it. We followed the consequences of that and said, that means it's not Cauchy. And now we've got that Sn is Cauchy and Sn is not Cauchy. That's no good. So we must have made a mistake somewhere. It must have been right here where we said maybe Sn is not bounded, right? So we say, okay, this assumption was bad. It doesn't work. We've got to conclude then that Sn is bounded. Yes?
We can always assume there's some value to the right that's bigger.
You can always assume there's some value to the right. Yeah, I can. It's because there's a finite number of points. Yeah, so for that, that's a good question. All right. You know, we know unbounded means there's some value such that it's bigger than any ceiling. Why could I assume m is bigger than n? So what I did here was to say I can find some m such that Sm is bigger than or equal to the maximum, say, of S1, S2, Sn, and Sn plus 1. Right? And this is a finite number of things in here, so this maximum exists. Right? And then we look at this and say, well, Sm, we can say even bigger than this. Sm is not S1 because it's bigger than S1. It's not S2 because it's bigger than S2. Right? It's not Sn because it's bigger than Sn. So we must have that m is bigger than n. So yeah, it's a good question. Any other questions on this lemma? Okay, so again, the lemma is, okay, it's there. It's not super interesting on its own, but it's going to help us toward our goal. And our goal is this main theorem, that if Sn is a Cauchy sequence, then it converges. Okay, so we're starting by assuming that we have a Cauchy sequence in hand. All right, I've given you a hint here that we want to use the fact that Cauchy sequences are bounded. So we know that Sn is bounded. So let's see, do you remember from last week, what was something that we know about bounded sequences? So I'll give you another hint. We have a sequence that's bounded above, for example, and since it's bounded below, it's certainly not diverging off to minus infinity. What do we know about that sequence? I have a limit superior, right? And similarly, I have a limit inferior. So that means there exists a limit superior, so S bar as the limit superior, and S underbar as the limit inferior. Okay, and these are finite. It's not like, the sequence isn't going off to infinity, so we're not going to have a limit superior that's trying to blow up on us. These are solid, finite, real numbers. All right, I don't have any sense of what my S is going to be, right? But what I can hope, we're trying to prove this thing is convergent. So what are reasonable numbers for my S to try here? Yeah. S bar and the S underbar, right? Those are I don't have any other way to guess at an S. So I'm hoping that these are the limit. In particular, we said it's actually enough for these to be equal to each other, right? If the least upper bound and the greatest lower bound in the limit are the same, then in the limit, my sequence is going to be sandwiched in between these two things. And it will also converge to these two things. So it's enough to show that these guys are equal to each other. Okay, and then the limit would also be S bar. So that's what I'm going to do. I'm going to try to look at the difference between these two things and show that it has to be 0. Okay, so we know that we're going to be using the fact that this is a Cauchy sequence. So I'm just going to grab an N and an M straight away, and they're going to have to fit in there somewhere. So let's consider N and M that are natural numbers. We'll decide later what they should be exactly. Okay, but we can certainly write this. So I want to start by looking at this difference. I would like to show that this difference is equal to 0, right? If I can show that difference is equal to 0, then I'm in business. Then these two numbers are the same. But I need to rearrange this a little bit. I need to put this in terms in my sequence, in terms of things that I have some ability to actually put bounds on. So as our hint, we know that Sn and Sm should be showing up in there. So let's just start inserting them in here. So I'm going to say I'd love to have an Sn show up in here. That means I'd better add it back. And I'd love to have an Sm show up in here. Right? This is a good term to work with because this is the term that's going to show up in our definition of Cauchy sequence. That means I need to add it back. And I still have this term here. So I did all this addition and subtraction just with the goal of making this term show up somewhere because I know I have to use the fact that we're working with a Cauchy sequence, right? If I leave out this point and then just say if Sn is a sequence then it's convergent, then that's nonsense, right? I've got to use this. So that's why I add these terms in, and then I just subtract them off again. OK, and then hopefully to nobody's surprise, I'm going to use triangle inequality. OK, so I'm going to have S bar minus Sn, Sn minus Sm, and Sm minus S underbar. All right, we've got to start using our definition now, right? That means I need a tolerance. I need an epsilon. So I'm going to choose my epsilon. And we know we're working with the Cauchy sequence. So we know we can get an n star from that. There exists some n star such that if n and m are bigger than n star, then this difference can be made small. Let's call it less than epsilon over 3 just for fun, because we've got 3 terms floating around, so why not? So I know if n and m are big, I can make this term as small as I like. Can I make this term small? So just tentative nods. So the answer is going to be yes, but be careful, right? We don't know anything about the sequence converging to S bar, right? So it doesn't mean that any big value of n will make this converge to S bar. But what do we know? We know that no matter how big this n star is, I can always find an n that comes up close to it again, right? Because this is my least upper bound in the limit, right? It's not only an upper bound, but it's the tightest upper bound I can find. The sequence keeps getting close to it again. It might deviate away, but it gets close again. So it is not true that any old n will make this small necessarily. It is true. So since S bar is the least upper bound in the limit, that means that I can at least find a value of n such that this term is small. It's not always small, but it's sometimes small. Okay, we're going to get the same deal happening over here. S underline is my greatest lower bound in the limit, right? And that means I have a sequence which this is acting as a lower bound in the limit for. The sequence might bounce around up here a lot, but it always has to come back and get close to this again. And then n gets bigger. It may bounce around, but it has to come back and get close again. So we can do the same thing. We also know there exists some m such that Sm minus S lower bar is less than epsilon over 3. Okay, so I'm not making this inequality work for all possible values of m and n. I'm just picking one choice of m and one choice of n that make them work. And the good news is these are big values in n and m. They're specific values, but they're large. So they'll still preserve this inequality, right? We're in business with our Cauchy sequence. So let's try to put this all together. Okay, so we have that S bar minus S underbar, we said was bounded by this. For this particular choice of n, this term is certainly less than epsilon over 3. Again, it's not true for all n, but it's true for this value. Okay, this particular choice of n and m happen to be large. They happen to be bigger than our n star. We guaranteed that. So this term is also less than epsilon over 3. Okay, and then finally, this particular choice of m was good enough to make sure this term is small, less than epsilon over 3. So I can bound that by another epsilon over 3. Okay, so what do we have? We have that we picked any epsilon, as small as you like. The difference between these two terms is less than epsilon for any epsilon. So this holds for every epsilon that's a positive number, no matter how small. So if it holds for every epsilon, what can we conclude about this difference? This difference vanishes. This is 0, right? Because this difference is smaller than any positive number you like. If it's smaller than every positive number, then we can conclude that s bar minus s underbar is actually equal to 0. So these numbers are equal to each other. Right? So we said last class, if these numbers are equal to each other, this upper bound and lower bound in the limit are the same, then our sequence in the limit is going to be sandwiched in between them. And it's also going to converge to the same thing. So we can conclude Sn is convergent. Okay, so every time you're given a sequence, you're asked to prove it converges. You have choices. You can use the definition of the limit, and that's fine if you can guess at the definition, guess at the value of the limit. And sometimes that's easy to do. You can say, I'm not sure what the limit is. I'm just going to try to prove this is a Cauchy sequence, and that might be easier because again, you don't need to guess at the value of the limit. Or a third choice, I guess, would be you could say, I'm going to compute these limit superior and limit inferior, and I'm going to show they're equal to each other. That would prove convergence, right? So you have these tools in your tool chest. And again, you do what's easier. If it's easy to guess the value of the limit, then using the definition of the limit might be easiest. If it's not clear what the value of the limit is, then proving something is a Cauchy sequence is a very powerful technique for proving this kind of convergence. And on the flip side, if you want to show something's not convergent, well, you can show that the definition of the limit breaks, or you can just show it's not a Cauchy sequence, right? And that tells you not convergent. So you have these tools. Any questions on that? All right, so let's do an example of this where I don't know ahead of time what the limit's going to be, or if there is a limit. Okay? So this is fixed point or root finding problems. So we want to solve f of x is equal to 0. Okay, a common approach is to rearrange this, somehow get an x over onto one side of the equation, and have whatever's left on the other side of the equation, and then try to iterate. So xn equals g of xn minus 1. And you hope that this iteration converges. So you make a guess at x naught, which may be closer, may be far from what's the true solution. Plug it in, and you get a new value. Take that, plug it in, you get a new value. So for example, find the positive root of say, x squared equals x plus 2. Could rewrite as x is equal to the square root of x plus 2. Right? So I've got an x on one side of the equation, some function on the other side. This becomes my g of x. And then you start iterating. You do this process. Xn plus 1 equals the square root of xn minus 1 plus 2. And you hope that as you do this, these values of xn, that you get closer and closer to an actual solution of this thing. So we hope xn converges to the root of the original problem. But it might not, right? You're generating a sequence, and it might just bounce around forever and never settle down anywhere. If it settles down somewhere, it should settle down to a solution of this problem, xn minus 1 equal to xn. But it might not settle down. It might blow up. It might just bounce around forever. We don't know. And we want to prove that this converges. Okay, so here is our little fixed point iteration theorem. Okay. So suppose there exists some real number such that f prime always stays less than this number, which happens to be less than 1 for all x. Then the sequence generated like this converges. Okay, and this would be a typical kind of analysis you'd do for a numerical method, right? You build a method, you want to show it converges. Again, you have no idea ahead of time what the limit of this thing is going to be, because if you knew that, you wouldn't be doing numerics. But you say, okay, I can build some sort of iteration that seems reasonable. I know what this function is. Okay, in this example, it was root x plus 2. It might be something else. I know what this function is. I might be able to compute its derivative and get some bounds on that. And hopefully that's enough to guarantee that when I run my code, it's going to compute the right thing. Okay, and we want to do this by showing this is a Cauchy sequence. So we're going to choose an x naught to kick off this iteration. Okay, and define these things as we have above. Xn equals f of xn minus 1. So this is our sequence. We get a sequence x naught. It gives us x1. It gives us x2. It gives us x3. We have a sequence. All right, so we want to show it's a Cauchy sequence. I'm going to start by looking at what happens to the difference between neighboring terms. We know that looking at the difference between neighboring terms is not good enough for convergence, but it's easier to get bounds on. So I'm going to start by bounding the difference between neighboring terms, and then we'll try to stack them together to get a Cauchy sequence. So we know this. We know that xn minus 1. This we computed. Okay, it's written here. This we computed using our last term. Yes? And this we also computed by using our previous term. This is f of x n minus 2. So I have function values showing up. I know I expect to use the value of the derivative. How can I make the value of the derivative appear here somewhere? Mean value theorem, right? So we know that this is going to be equal to xn minus 1 minus xn minus 2 times f prime of c, okay, for some cn between xn minus 1 and xn minus 2. That's your mean value theorem. Okay, and we know this value of f prime behaves itself, right? It stays less than 1. It stays less than r. So we can say, actually, xn minus xn minus 1 is always less than or equal to r times xn minus 1 minus xn minus 2. And then I can keep going and I can keep marching backwards, right? So I said this difference between these two neighboring terms has a bound that depends on r and the previous two neighboring terms. I can do that again to this. I can say this is less than r times xn minus 2 minus xn minus 3. I can work backwards. So this is less than r squared xn minus 2 minus xn minus 3. And then I could do this again and again and again. I can keep marching back until I get to my x1 minus x naught, and then I have to stop. So we're going to keep going with this. And at the end of the day, we're going to get r to the n, x1 minus x naught. And this is nice because this is a lot easier to control than just some general xn minus x minus 1 that came from some complicated function. Right? This came from a complicated function iterated many times. These are just two numbers times something less than 1 raised to a power, which we know this is going to go to 0. We know that having that go to 0 is not enough to guarantee convergence, but it tells us how neighboring terms are related to each other. And now, again, we're going to try to bootstrap our way along and find out not how next door terms are related to each other, but how arbitrary terms are related to each other, because we're trying to do Cauchy sequences. So what we need to look at xn minus xm in general. Let's say for m bigger than n. We're doing Cauchy sequences, we're doing convergence, so we should have an epsilon. And we start to write this down. OK, again, this is something complicated that came out of applying this function a whole bunch of times. This also came from applying this function a whole bunch of times. It's not that easy to write down exactly what these are. So I'm going to do what I always do. I'm going to put these in terms of things that I know something about. I know something about how neighboring terms are related to each other, right? So I could compare xn to xn plus 1. That would be easier because I know how those are related to each other. That means I need xn plus 1 to come back. I could compare xn plus 1 to xn plus 2, because I know how those are related to each other. I need to add that back. And I could keep going, right? This is the bigger index. So every time I add another term here, I'm getting closer and closer to m. So I could keep going with this. And at some point, I could say, I subtracted off an xm minus 1, and then I added it back on. And then I still have this minus xm at the end. OK, so it's a long string of terms, but it's a string of terms that this I know how to bound, this I know how to bound, this I know how to bound. All of them I know how to deal with. Of course, we have to separate them out. Just triangle inequality. It's almost the only thing we've done today is the triangle inequality. So xn minus xn plus 1, xn plus 1 minus xn plus 2, all the way down to m minus 1 minus xm. Okay, this is less than r to the n, x1 minus x naught, r to the n plus 1, x1 minus x naught, all the way down to r to the m minus 1, x1 minus x naught. That was the estimate that we did over here. That we said all of these terms, difference between neighboring terms, we could put in terms of the difference between our starting terms. Yes?
Remember that there we started with xn minus xn minus 1, and here we have like xn plus 1.
So what was it here? The biggest index shows up here. We can, sure, we can correct those. Okay, and then we start simplifying and trying to factor the way we've done before, right? So again, it was obviously an x1 minus x naught floating all the way through that we can factor out. There's also a whole bunch of powers of r that are floating all the way through, and we can factor some of those out. So let's hold some of those out. And we get a 1 plus r plus r to the m minus n minus 1. Okay, so let's fix n for a minute. And we're going to let m get bigger and bigger. What do we know about this? What's that? It looks like a geometric series, right? So this is a geometric series. And it's monotonic, right? As m gets bigger, the value of this gets bigger. So as m grows, this sum also grows monotonically. Right? And so it grows monotonically and hits its limit, and the limit as m goes to infinity. What's the limit of this thing? You remember? 1 over 1 minus r. So it grows monotonically towards 1 over 1 minus r. Right? So since it's growing towards that, any fixed term is less than the limit. So for any m bigger than n, the sum is less than or equal to 1 minus r, right? Because as we add more terms, it gets bigger and bigger and bigger and approaches this value. If we haven't added infinitely many terms yet, we're still under that value. Okay, so if we use that, again, we're trying to show this is a Cauchy sequence. We have xn minus xm. Now we have a bound on this that doesn't depend on m or n, which is convenient, right? This is complicated, but we can bound it. We don't need to know exactly what it is. We just need bounds. So this is going to be less than or equal to Rn plus 1 times x1 minus x naught divided by 1 minus r. right? So it's just simplifying. And again, the same trick that we're always trying to do, right? We write down the terms, xn minus xm. We say, let's try to put this in terms of things that we know how to deal with. We knew how to deal with neighboring terms. And then see if we can simplify things so that we don't have so many m's and n's floating around. This is pretty simple now. I've got n showing up in one place, which is good. Can I make this less than epsilon? Yeah, probably, right? So this is less than epsilon if we do what we did before. N is going to be bigger than, let's see if we can do this correctly, log of epsilon 1 minus r over x1 minus x naught divided by log of r minus 1. And this becomes my n star. Right? So we've taken this really complicated sequence. Complicated sequence is generated by a numerical method for trying to solve a problem. I have no idea ahead of time what the limit's going to be. If I knew the limit, I would not need to do this analysis. But since Cauchy sequences don't require me to know the limit, they just require me to be able to compute the terms, I can do this calculation. I can say I can look at arbitrary terms, and as long as things are big enough, bigger than this value of n star, I can force this to be less than epsilon. So I say, great. That means that xn that was generated this way is Cauchy, and therefore it converges. Okay, so it's a nice example. It's nice to see a more realistic example, not just a toy example where you say, well, I knew that converged anyways. And these are standard techniques that you'd use in applied math.